So, good morning, everybody. Let me begin by thanking the organizers for the kind invitation to participate in this workshop. Not only giving me an opportunity to present a talk, but also to come back to the beautiful Natal. For someone coming from the dark and cold and rainy Scandinavia, this is paradise. So I'd like to tell you about some recent work I've done with my student, Alexander Balabanov, on robustness of symmetry-protected topological states against time-periodic perturbations. And embarrassingly, there is a misprint already on the first slide. The boldface is on my name. It should be on Alexander's name, because not only has he done all the heavy computations, but also contributed some of the key concepts in this project. So with that said, let me begin by providing a brief background and motivation. And I think I can be quite brief, because we heard several talks this week touching on various aspects of the topological quantum matter. The problem I will discuss belongs to the realm of symmetry-protected topological phases. And this is one of the two major classes of topological matter. This is one class, the other we call topologically ordered phases, which are more exotic. They have strange properties like long-range entanglement and fractionalized excitations and all kinds of stuff. This class is much larger. There are many more known realizations of symmetry-protected topological phases. And the defining property is that the bulk is gapped. So this is a schematic of a sample. This is the bulk, and the blue thing is a surface. The bulk is gapped with a ground state, which is characterized by a non-zero topological invariant. Now, to identify and to compute a topological invariant is by no means trivial. It was done first time in the early 1980s by David Thouless, collaborators, for the integer quantum Hall effect. I was awarded a Nobel Prize last year. Or to be precise, 1/4 of last year's Nobel Prize in physics was awarded for the first computation of a topological invariant. But to cut a very long and technical story short, a many-body ground state for non-interacting electrons, say, can be built from single particle states. And if you go to a K-space formulation on the lattice, that will be the block states. And the way the block states behave as one moves around in the Brillouin zone can be coded in a mathematical object called the Berry curvature. So either you know about this or not, but it's not important for my talk. Anyway, this object, if integrated over all the occupied states in the Brillouin zone, that integral will be an integer. We are guaranteed to have an integer by the Chern theorem. And if that integer is 0, well, then the phase is trivial, topologically trivial, something that we can understand with textbook physics. If it's a non-zero integer, well, then we call it topologically non-trivial. So it's a very elusive property. It's nothing that stares you in the face. It's really a kind of hidden property. One has to work hard to uncover this property, which explains why it took us so long in physics to actually arrive at it. But it has profound implications for the physics. And maybe the most important is the so-called bulk boundary correspondence. That is, if a system has a non-zero topological invariant, that signals the existence of states, in-gap states, states with energy in the bulk gap, living at the boundary, with the property that these states are robust against any perturbation which preserves the underlying symmetry or symmetries of the problem. Provided there are two provisos here, the perturbation has to be local, and it should not be too large. It cannot close the bulk gap, because the gap is there as a protection. And since this is now a workshop on quantum devices, I should maybe already here say that this symmetry protection of boundary states, it's the property that makes these phases interesting for future technologies, for possible future applications. There have been many, many proposals and ideas ranging from spintronics to topological quantum computation, and all of these applications, possible applications, rely on the symmetry protection of boundary states. And moreover, these boundary states frequently have interesting properties. It's not just that they are robust against large classes of perturbations, but they have interesting properties that can be utilized in various technologies. So one example, a quantum spin Hall system was predicted and discovered 2006. So it's a two-dimensional quantum well in a semiconductor heterostructure built out of mercury telluride. So the interior is insulating. It's a topological insulator. But it's also topological, meaning that at the boundary there are states, boundary states that are free to move, with the property that spin and momentum are locked, that we heard about in Professor Mallard's talk Wednesday. And this property is protected by time reversal symmetry. So if one perturbs these boundary states by perturbation which respects time reversal symmetry, nothing will happen to them. And this is the reason why people have gotten very excited about this class of systems. So the ITRS, I think it means International Technology Roadmap for Semiconductors. It's an international body that advises the semiconductor industry. They are picking up on this. So in last year's report, they have a big chapter in the annual report where they advertise these systems as very promising platforms for dissipation-less spin transport in semiconductors because of the spin momentum locking. And the dissipation-lessness here, that the electrons are free to move, comes precisely from the symmetry protection. Another example that we heard about from Professor Katsura's talk and also Professor Mallard's talk Wednesday are the one-dimensional P-wave superconductors. So these systems also host boundary states, which are the Majorana zero energy modes with interesting properties. They have non-abelian statistics. And these states are now protected by particle Hall symmetry. And this has given rise to a lot of excitement and work trying to utilize these systems in topological quantum computing. And maybe you can tell from my little cartoon here that I think at this stage of development, this is very interesting for basic physics, but whether we are close to a topological quantum computer, I'm a little bit more skeptical, but anyway. So these are two examples, and there are many, many more possible and realized examples, all sharing the property that the Hamiltonians of these symmetry-protected topological phases, they belong to equivalence classes, symmetry classes, specified by three symmetries. In this row, time reversal invariance, particle Hall symmetry, and what we call chiral symmetry. So given the presence or absence or the type of time reversal, particle Hall, and chiral symmetry, we can form these various classes, and then depending on the dimensionality of the system, we can predict the topological properties. So a zero here means that a system does not have time reversal. Plus means that the square time reversal operator has eigenvalue +1, here it's -1, and similarly for particle Hall and chiral symmetry. And the chiral symmetry will play some role in my talk. So for the purpose of my talk, you should think of chiral symmetry as a kind of sublattice symmetry. It means that a Hamiltonian that is chiral symmetric, it has the property that it does not connect states on the same sublattice. So if you have a tight binding model with, say, nearest neighbor hopping, fine, chiral symmetric. But if you add a chemical potential or a next nearest neighbor hopping, you break chiral invariance. And then you go in here and you check the dimensionality, 1, 2, 3. If you're adventurous, you can go all the way up to 8 dimensions. This is mathematical classification of random matrices that have been applied to this field of physics, and you can read off whether there is a topological phase or not, and also the character of the topological invariance. So for example, if I go into this BD1 symmetry class, This is the class of Hamiltonians with time reversal, particle hole, and chiral symmetry. In one dimension, yes, there's the possibility of a topological phase with a winding number topological invariant. But if you go to higher dimensions here, 2, 3, and 4, there is no such topological phase. This means also that if I know the symmetry class to which the system belongs, I can also read off what kind of perturbations under which the boundary states will remain robust. So again, if I go into here the BD1 class, if these symmetries are respected by my perturbation, fine, I will stay in this. If I'm in this non-trivial topological phase with boundary states and perturb with the perturbation with the symmetries, I'm guaranteed to still have the boundary states with all their properties intact, provided again that the perturbation is local and doesn't close the gap. In fact, it's often sufficient that one of these symmetries is preserved. We don't have to preserve all of them. Okay. Now, the standard theory, topological band theory, tells us about the behavior of the boundary states, or how they respond to static perturbations. So one may now inquire, what about time-dependent local perturbations? If I have an environment with perturbation that varies in time, how then will the boundary states behave? Are they still robust? And one can approach this problem in many different ways. In this project, we have been kind of opportunistic and specialized to the case of time-periodic local perturbations. Opportunistic because for this case, we have a powerful tool, a method, a mathematical machinery by which we can address this problem in a well-defined way, and that is Floquet theory. So let me say from the outset that by going to Floquet theory, I'm shifting perspective from ordinary topological band theory with energy bands and block states to band theory for quasi-energies and the corresponding Floquet states. And now, if you haven't heard, or if you're not so familiar with Floquet theory, what I just said probably sounds a bit cryptic, so let me back up a bit. So Floquet theory is a piece of mathematics, a piece of the theory of differential equations, which in fact all of us have some acquaintance, indirect acquaintance with from Bloch's theorem. But Gaston Floquet was much earlier than Felix Bloch. Applied to a time periodic Hamiltonian, the period capital T, Floquet tells us that the solutions to the Schrödinger equation come in this form, where the U and T, this factor here, are periodic eigenstates of the time evolution operator. And the dynamical phase is parameterized by so-called quasi-energies defined modulo 2 pi over T. So there's a periodicity built in here because the drive is periodic. So these so-called quasi-energies will now play the role of ordinary energies and parameterize the dynamical phases that's acquired by the system. Now, to obtain the spectrum of quasi-energies, one diagonalizes the time evolution operator. That's one way of doing it. Another way is to Fourier transform from time to frequencies and diagonalize corresponding infinite dimensional Hamiltonian, which is difficult, so one typically truncate that Hamiltonian, so that's another way of doing it. I will show you a little bit about that later. But the important thing now is that these quasi-energy spectra, they have a band structure. And this band structure can be characterized, again, with topological invariance in exact analogy to ordinary band theory. And this has now led to a large effort by many people to try to identify or propose various ways of driving systems periodically into a non-trivial topological phase. And here are the two starting papers here. So this is a very different way of thinking and approaching the problem of topologically non-trivial phases by driving the topological trivial system or phase periodically and creating a band structure of quasi-energies with non-trivial properties. It's important to say now that this is not just a pipe dream of theorists. This has been realized in the laboratory. Here are two examples. A photonic lattice made up of an array, coupled array of helical waveguides, and the light is trapped inside this lattice but can move around. The photons can be transported around the edge of the lattice. So this is like a photonic Floquet topological insulator. Another example is by shining laser light, pumped infrared laser light onto a three-dimensional topological insulator, and that will hybridize photons and the excitations of this topological insulator, which are Dirac fermions. So one obtains photonically addressed Floquet states, and one can actually monitor and see the quasi-energy spectrum by doing ARPS, angular resolved photo emission spectroscopy. Very beautiful experiment. So it's not just a fantasy. It's something that can be done in the laboratory. Although I would say things are at a very early stage. There's much, much more to be done, but a very promising avenue. Now, there's one important difference between ordinary topological band theory and Floquet band theory, coming from the periodicity of the quasi-energies. So if you look at this example with a two-dimensional system, well, the two-dimensionality is not important here, but a Floquet system, a periodically driven system with, say, two bands, like this, here plotted in the first periodic zone, quasi-energies. You see there's a gap here around zero quasi-energy, which may host a boundary mode. But now, because of the periodicity of the quasi-energies, there is a second gap, stretching from the top of the upper band to the bottom of the lower band. And that so-called anomalous gap may also host boundary modes. So to keep track on these different boundary modes and to count them and make sure that one is doing things right, if one is to predict something, one has to properly assign two topological invariants, one to the normal gap and another invariant to the anomalous gap, counting how many such boundary modes are present. And now the type of Floquet topological invariants will depend on the dimensionality and the protecting symmetries, precisely similar to static systems. And if you like to learn a little bit more about this, this is a very nice paper by Nathan and Rudner discussing in a very pedagogic way how to think about this. Okay, so let's now go to our problem, where we use Floquet theory to study symmetry protection against time periodic perturbations. So here we start with an unperturbed Floquet system, a periodically driven Floquet system, say a topological insulator. And then we perturb this system by a time periodic perturbation with the same period as the drive of the unperturbed system. So this is the object that we want to study. And we want to understand how this time periodic perturbation will now affect the boundary states. And the case study we have mostly investigated is a harmonically driven Suschiefer-Heger model, or SSH model. And those of you that are like me, a little bit the elderly generation, you know very well the popularity of this model back in the 1980s. I think it was suggested by Suschiefer-Heger in 1979 and as a model for polyacetylene, and it turned out that this simple model here with the Hamiltonian has some very interesting properties. And this very model is now enjoying a kind of renaissance in this field of symmetry-protected topological phases, because arguably it is the simplest model supporting a non-trivial topological phase. So it's like a fruit fly of this field, or maybe not fruit fly, I should say, maybe Ising model or hydrogen atom of this field. So it describes a chain of atoms, each atom having a spinless electronic orbital, half-filled, with electrons hopping from site to site, and the lattice is staggered. You can think of it as the atoms having alternatingly different distances. So there are two hopping amplitudes, gamma 1 for hopping within a unit cell, and gamma 2 across two unit cells. So that's the standard ordinary SSH model. And what we do now is we drive it harmonically. That is, we modulate the hopping amplitudes by a time periodic function, which we take here as a cosine. You see here gamma 1 minus Vt, gamma 2 plus Vt. This is how we set up the model here. Now, before I go to discuss perturbations of this harmonically driven model, it's instructive to take a step back and look at the original time-independent SSH model. So I put the drive to 0. And as it turns out, this model belongs to the so-called BD1 class. It has time reversal, particle Hall, and chiral symmetry. And the important symmetry is chiral symmetry. This is what protects or rather predicts the existence of boundary states. And chiral symmetry I can express by passing to a first quantized formulation. So I pull out the block matrix in K-space. And then the chiral symmetry is encoded by this relation here, where sigma z is the representation of the chiral symmetry operator in K-space. And sigma c is just the ordinary C Pauli matrix. And if a Hamiltonian in K-space first quantization satisfies this, yes, then we have chiral symmetry. And the important property is that this implies that all eigenstates have a partner with opposite energy. That's the thing that's the important consequence of chiral symmetry. Now, if I cut the chain open, I will find that if the intracell hopping vanishes, then the SSH chain has a localized zero energy state at each boundary. This is very simple to show, much in the same spirit as Professor Katsura showed for the Kitaev chain. This is, I can do in a few lines. Now, moreover, as it turns out, this model has a topological non-trivial phase with a topological invariant, winding number invariant, as it turns out, equal to unity, as long as the intercell hopping gamma 2 is larger than the intracell hopping. So by the bulk edge correspondence, this implies that there is precisely one state at each boundary. And now if I put together these three facts here, 1, 2, and 3, it follows immediately that in the whole topological phase, in the symmetry-protected topological phase, this system is guaranteed to have boundary states with zero energy. The zero energy property is protected by the symmetry. And again, it's important now to remember that when discussing this protection, one has to make the I'm discussing that in the next slide. This is still the time independent. It's coming. So it's important that the perturbation that by which we probe the robustness is a local perturbation. So you imagine you have your chain and you have one boundary with a state, and then you apply a local perturbation at one boundary, and you try to take that state away from zero energy. Well, by chiral invariance, we will then have to produce a partner state with the opposite energy. But that would give you two boundary states at that boundary, which is impossible according to the topological invariance. So that's a very simple argument why you have this protection. So it's important to understand that this symmetry protection is kind of an interplay between topology and symmetry. But symmetry is crucial here. Without it, it doesn't work. Now, coming to your question, let's now pass to the time-dependent model. And for the periodically driven, harmonically driven SSH model, the chiral symmetry protection now applies to the Floquet states, encoded by this relation for the time evolution operator, where again the symmetry operator in K-space is just a sigma Z Pauli matrix, like so. And in our paper, we prove that a sufficient condition for having this property is that the time periodic Hamiltonian in first quantization in K-space satisfies this relation. And this is a little sketch of the proof here, which I'm not going into here now. Maybe the more mathematically inclined people here in the audience, if you are curious or if you are interested, if you're looking for a good problem, it would be very nice to prove that this condition is also necessary. Because if so, we would have a much simpler characterization of symmetry protection for a time periodic Hamiltonian. But we failed to show the necessity of that condition. It's sufficient, but in the other implication, we haven't succeeded. It's here even. It's here even. Even, yes. Yeah, of course, you need your unit cells too. Didn't I mention that? I think it was on the slide, but okay, no, it's even. Okay. So given this, let us now look at the quasi-energy spectrum of the harmonically driven SSH model. So on the vertical axis, I'm plotting quasi-energies in the first, what's called Floquet zone, from minus omega over 2 to plus omega over 2, where omega is the driving frequency, versus I will disguise phases in great detail. It's a very important thing. Can you please allow me to a few more slides? There are no phases here. Let's put it that way. But I'm coming back to that question. It's actually one of my punchlines. No, it's a free model. Yeah, it's a non-interacting model. Just hopping. Just hopping. Oh, yeah. Let me show you. Yes, you see that there's one gap around zero quasi-energy, provided that gamma 2 is within this interval, fixed with gamma 1 0.15. So 0.15 is somewhere here. And then there's a gap also up here, the so-called anomalous gap. And both these gaps will support boundary modes, as you see. These are the quasi-energy levels for the two boundary modes, as predicted by the topological invariants for this model. So there's one invariant which we call nu 0 and one that's called nu pi, and both are equal to 1. So there's one such boundary state at each boundary. And this computation is quite technical and cumbersome, but essentially one discretizes the time evolution operator and then follows a method by these people here, but I'm not going into this here. Okay, so this is the unperturbed Floquet spectrum, and now the question is, suppose I perturb this by a time periodic perturbation, what will happen? So we expect that the boundary states will be robust under local time periodic perturbations with the same period t as the driving, provided that our condition, our sufficiency condition for chiral invariance is satisfied. And you see here I have written this relation in direct space. I'm using a representation of the chiral symmetry operator in direct space because my perturbation is local and I want to allow for disordering and nasty stuff, so I don't want the Fourier transform here. And this is actually, I think, a better way of really thinking about the chiral symmetry, which I already told you about. You see, the chiral symmetry operator is nothing but the difference between projectors onto the two sublattices. There are two sublattices A and B, and symmetry operator is simply the difference between these two. All right, examples of such time periodic perturbations satisfying this condition. One example is to spatially disorder the hopping amplitudes locally, close to a boundary. So I replace the hopping amplitudes, the uniform hopping amplitudes in the interior here. When I get close to the boundary, I replace these uniform numbers by some random distribution. So I disorder the amplitudes, and then I drive them with a time periodic modulation, which is now an even function of time. That's important for this relation to be satisfied. Another possibility is to add the time periodic disordered staggered chemical potential, again close to boundary, and disorder the amplitudes. And now to satisfy this condition up here, I have to choose an odd periodic modulation, like so. So these two examples, they may not be the most realistic for laboratory physics, but they are very convenient to work with for a theorist. And I will come back to how one can improve things for more realistic perturbations a little bit later. But let's stay with these simple perturbations now. All right, so now if I take my Floquet SSH model and hit it with one of these perturbations, so here I add a perturbation of the intracell hopping, drive it with a cosine. Here I do the same, but for the intercell hopping, and here I disorder this staggered chemical potential close to the boundary and drive it with a sine function, because I need to satisfy chiral symmetry. And you see nothing happens to the boundary modes. They are untouched by the perturbation, as expected. This is how it has to be. Now contrast this to the case where I have shifted the phase. And now I come back to Professor Wigman's question about phases. So now I have turned my cosine into a sine. Here a sine, and I turn the sine into a cosine, and then I violate chiral symmetry. And you see, indeed, the effect is dramatic. Bad perturbations here of the boundary modes. And now some of you may say, well, what's the big difference between the sine and the cosine? There's just a difference between a phase, pi over 2. In this context, it means a difference or a new choice of zero reference time. I can choose to start my clock a little later, and then I turn the sine to a cosine. So how can it be so different? Well, if I do that shift of phase, I will have to do the same for the bulk, for the driving of the bulk, and then I lose chiral symmetry of the bulk, so it doesn't work. So the take-home message here is that the robustness of boundary states depends critically on the relative phase between bulk driving and perturbation. That's all that matters. All right, Floquet theory can also be applied to time-independent models, for the simple reason that a time-independent model is trivially periodic in time. It doesn't know about time. So here I plotted the energy spectrum, the ordinary energy spectrum for the time-independent SSH model in some arbitrarily chosen intervals. I just pick a parameter, which I call omega, and then plot the spectrum as a function of my intercell hopping, keeping all other parameters fixed, and this is what it looks like. These are now energies, and here's the boundary state. And now I can convert energy to quasi-energy by imposing a periodicity on the spectrum, and that I have the quasi-energy spectrum. And this is an exact analogy to how we do it for momentum, when we turn momentum into crystal momentum or quasi-momentum by imposing a periodicity from the lattice. Think in terms of this empty lattice model that we discuss with our students. And then by folding the periodic spectrum into the first Brillouin zone, we get band structure. And here I do the folding into the first Brillouin zone in energy, what's called the first Floquet zone. So then I get this kind of spectrum for the quasi-energy. So this comes from the imposition or having imposed periodicity on the spectrum. And this is to be compared to the harmonically driven SSH model. And you see it looks not too different, but there's an important difference that since this is done by hand, so to speak. There is no periodic driving. I lose these anomalous boundary states. They are not present in the time-independent model. All right, so given now a time-independent model, like the time-independent SSH model, let me now subject it to the same time-periodic perturbations that I showed you before. So what do we expect? What about the robustness then of the boundary states? For this case, well, we expect, since there's no bulk driving, there's no constraint from a relative phase, and therefore one expects that the boundary states are robust against a much larger class of perturbations, provided, of course, that there is one phase, one choice of phase, one reference time for which the perturbation is chiral symmetric. So let's see if it works. This is our very simple prediction. So here's the chart of perturbations for the case of the Floquet-driven topological insulated, the non-trivial phase of the Floquet SSH model, subject to these various perturbations, like here. So let's now look at the upper row, where I replace the periodically driven model by the time-independent SSH model. You see, I get this. I lose the anomalous mode, as expected, but the one in the normal gap is untouched by the perturbation, just as I expect. Now the graphs looks a little bit different here because these are line plots and these are scatter plots, and also there is some little larger effect on the bulk states from in the case of the time-independent model, which I'm not going to discuss here. So that's entirely expected. Now look at the lower row. Here we had a dramatic effect when we applied these perturbations to the time harmonically driven SSH model. So now I replace the harmonically driven SSH model by the time-independent SSH model, and then I get this. No effect on the boundary modes. Because now I can shift my phase. Now I can turn my sine function to a cosine function by changing to a new zero reference time. Because the theory, the bulk theory, the unperturbed theory, the time-independent SSH model doesn't know about time. It doesn't care about which reference time I choose. So I think the proper way to think about this is to say that if you have a static time-independent model that you want to treat within the Floquet formalism, the proper way of thinking about it is that if there is a symmetry, like a chiral symmetry, there is actually an infinite number of chiral symmetries, one for each choice of reference time. So the take-home message here is that boundary states of chiral invariant static systems are robust against all time-periodic perturbations, which respect chiral symmetry for at least one reference time. So what I have shown you so far is more or less expected. I think anyone who would sit down and think about the problem would carefully predict this, and all credit we can take for this is that we brought this out in the open, so to speak. But the results are not surprising. It's how it has to be. But at this point, we were up for a surprise, a big surprise. And this takes me now to the second half of my talk. The time-independent SSH model, or for that matter, any time-independent, symmetry-protected, chiral symmetry-protected system will have boundary states which are resilient against a large class of symmetry-breaking local time-periodic perturbations. And this is unexpected. Given our intuition drawn from topological band theory, we say that as soon as we break the symmetry of a perturbation, well, then things go bad. But as I will now argue, if we drive the perturbation periodically, we will suppress the effect, sometimes suppress it so well that the states remain robust. And again, since this is a conference on quantum devices, the little connection possible I can make is that if we want to keep a system protected from environment and reduce effects from decoherence and keep in particular the boundary states intact, and there are symmetry breaking perturbations around, if we can somehow find a way to drive these perturbations periodically in time, we may get rid of them. So that maybe a little bit of science fiction idea, but you know, today's science fiction is the science of tomorrow. So maybe this is what one could hope for. So let me try to show you what's happening here. So to be very, very concrete, let's consider perturbations belonging to this class here. So V sub n is a local perturbation satisfying this condition, where again gamma is the chiral symmetry operator in real space. If there's a minus sign here in this relation, yes, then the local perturbation satisfies chiral symmetry. If not, if there's plus sign, chiral symmetry is broken. But the important effect from the important symmetry breaking effect comes from adding these time periodic modulations. So you see, as I go higher and higher in the sum, I'm adding higher and higher harmonics like this. And you will see that this class of perturbations generically break chiral symmetry for all choices of reference times. There's no way you can find a phase that will make the perturbation chiral symmetric. I write generically here because maybe you can find some. We haven't exhausted this, but typically chiral invariance as encoded in the relation here is broken. So let's look at a few examples drawn from this class, applying perturbations of this type to the harmonically driven SSH model. And indeed, you will find that because the perturbations break chiral symmetry, the effect is bad. The boundary states are badly perturbed. Here is a really big effect, both the normal and the anomalous modes like this. But now compare this to the time-independent SSH model, and I get this. The same bad symmetry-breaking perturbations applied to the time-independent SSH model will have a neglectable effect. And if I were to zoom in here, maybe you can see it actually. You see that there are small wiggles here. So I'm not claiming that they are perfectly robust. The message here is that the effect of the perturbation is dramatically reduced. And if one puts in numbers, one will see that the reduction often is so strong, so from an experimental point of view, we cannot really distinguish it from perfect robustness. So one way of coming to grips with this and trying to understand some aspect of it is to resort to perturbation theory. So I can do Floquet perturbation theory, which is just like ordinary stationary perturbation theory, but where one replaces expectation values by time averages over expectation values over one period of the drive. And if one focuses on perturbations of the zero quasi-energy modes and turns the crank in this machinery, one will find that the very structure of the chiral symmetric unperturbed spectrum imposes constraints on the effect of the symmetry-breaking perturbations that are so strong that the leading corrections, the leading contributions to the quasi-energy shifts, the first and second order contributions, completely vanish. So to make sure that we haven't missed some minus sign or something here, we went back to the computer and checked this. So here is a plot of the quasi-energy shifts as functions of disordering amplitude, or to be slightly more precise, V here, if I choose a V here, V defines the interval within which I allow my hopping amplitude to vary randomly. And then I take 100 disorder realizations with that bound for V and pick the largest effect on the quasi-energy shift, and then I plot it. So this is the curve you get, and you see the red wiggles means I'm leaving the perturbative regime and I'm adding subleading corrections. And if I go to a cubic plot, you see in the perturbative regime where this little piece here, I have a straight line. So this agrees with the prediction that the leading order correction is cubic, and it's maybe even better seen in this picture here. So this will be contrasted to the Floquet SSH model, where the leading contribution to the shift is simply linear, and we see it very clearly here in the perturbative regime that you have a strong suppression. So this is a little bit of a first glimpse of what's going on. However, this is not the full story, and you can see it from the picture here. If you look at the scale, the vertical scale from 0 here to 0.24 for the static case, here the scale is from 0 to 0.2. So the suppression is significantly larger in this case, all the way out in the non-perturbative regime compared to this. So there's something else going on here. The perturbative result just gives us a little glimpse that there's something special happening here. But there's something much more fundamental here. Quasi-energy. Delta is the quasi-energy shift, the shift from 0 quasi-energy. The largest quasi-energy shift for that particular realization. Exactly. But if they are slightly shifted, and you know, if they gain quasi-energy non-zero, they may start to move around and do nasty things. So this is how we probe the robustness. So the perturbative results are not the full story. The resilience against chiral symmetry breaking perturbations frequently hold also in the non-perturbative regime, and also for many, many other types of perturbations. It's kind of generic. So what's going on here? As it turns out, the explanation is embarrassingly simple once we hit upon it. But we had difficulties to convince our referees. We had to fight very hard. They debunked our result in the first run. Let's see if I can convince you guys now in the audience. Our explanation of this kind of surprising, unexpected result is very simple. It's because of the freedom of choice of reference time for time-independent models. And I can think of it in the following way. If you have a symmetry-breaking perturbation, you slice it up in one piece which preserves chiral symmetry, and the other piece which violates manifestly chiral symmetry. And then you try to find the reference time where the manifestly symmetry-breaking piece is minimized. And this choice of reference time will put an upper bound on the effect of perturbation. And this we can do because the unperturbed theory doesn't care about reference times of phases, it's time independent. So provided that there is a choice of phase, a reference time, where the symmetry breaking piece is small, sometimes maybe it may even vanish. What looks like a bad, nasty symmetry breaking perturbation actually gives a negligible effect. So I wish I could say something about quantum devices, but no, I will not try that. And my time is out, so I just tell you that we believe that the ingredients to test these results in the laboratory, those ingredients are now available. There are many proposals for realizations of SSH model in cold atom physics and in one-dimensional optical lattices. It has even been realized already for a bosonic version of SSH model where people saw these edge states. And very excitingly for us is that just a few months ago there was a breakthrough where people could experimentally realize a periodically driven random disorder potential in one-dimensional optical lattices. So this is precisely what we would need to test our results. So with that, I thank you for your attention.